Hello everybody, it's Yasmin again. This is a new episode on ThatITShow, still filling in for Vedran and doing a little bit of 6502 light assembly learning. So before we start, I just want to introduce today's episode. I'm going to be going through Easy6502 website /ebook/learning simulator / everything that you need to know when you're starting with assembly in Easy6502. And I'm going to be trying to explain why should you do the assembly, how to do the assembly, and what are the first things that you need to know when you're learning how to program 6502 directly. But before anything else, let's roll the intro. Okay, now for the start. Easy6502 was not written by me. It was written by Nick Morgan, as you can see on the left, and it is a combination of an ebook and a simulator that was done to complement the ebook and to turn it into something interactive. The main thing about what we are trying to do here is that since this is an ebook and contains the information, the simulator is one of the best ways to start learning. When learning the assembly language, the only thing that is going to help you is going to be just trying. So there is no way for you to learn assembly language just by reading in a book. You need to start learning, you need to start testing it out, you need to start using simulators, you need to start thinking in assembly, because everybody who has ever done assembly language is going to tell you that assembly language requires your brain to adopt to a different type of learning or different type of thinking about how to program a computer. At the same time, the reason why we are pushing, or I am pushing for assembly language, is that it enables you to understand how the computers work from the top, from the down to the top. The bottom thing in the computer, or the lowest thing in computer, is the CPU. Assembly language talks to the CPU directly, and there are no intermediaries. When you're talking to the 6502 using the assembly, you are directly programming the CPU, you are directly telling it what to do, and there is nothing standing between you and the hardware. So at the same time, you are learning how to do the assembly language, and you are programming the hardware and understanding how the hardware should work. So what is 6502 or Easy6502? There is an introduction here that says why you should learn the assembly. I completely agree with Nick on this, and the reasons are multiple. Aside for the thing that I already mentioned, so the idea of getting to understand how the processor works by programming it, it's a useful way of exercising your brain. It's a useful way of learning something new that is going to help you in understanding how the complex systems of today work. So, for example, when we're dealing with, I don't know, Windows, Linuxes, or whatever, they're operating systems, but deep inside the operating system, or under the operating system, there is also assembly like this. It is this x86 assembly that is much more complicated, because the processors themselves are much more complicated. But all the things that you can learn by using 6502 are valid over there also, because 6502 and x86 just differ. The main difference between them is that the complexity of the chip, not the ideas. So for example, 6202 has 3 registers. CPU by Intel's or x86 CPUs have much more. They have caches, they have different things that 6202 doesn't have. But the way you're dealing with all of those is the same. You are directly putting things into the register. You're using a register as a way to store temporary data, and then you are performing simple instructions on simple parts of data and creating complex programs out of those. The first example that Nick is using here, and I'm going to just zoom in a little bit because I want to make this much easier to read, is the first program that he does and tries to explain the basic parts of the assembly in. Before we do that, I want to explain how the assembler that he's using works. Because this assembler and a simulator, because we're talking about 2 different things, is adopted in such a way as to make it easier to understand different things, and also it makes some assumptions because it wanted to create an environment that is going to be enable you to not only do the assembly but also do graphics. Okay, so the first part here, these buttons here, assemble, run, and so on, are the things that enable you to do or perform actions on the text that you inputted in the field here. The thing that you are going to do is that you're going to write your code in assembler here, and then once you press this button, this code is going to be turned into assembly language, into assembly, or it's going to be turned into hexadecimal opcodes and data that is going to be put into the memory. You can monitor the memory here by using this monitor. So for example, if we want to see what is inside the memory, we can take a look at it. And this means that we can reset it and see the memory here. Let's start with the location 800 and the length of FF. So we are basically starting at the 9th page of the memory. Remember, we are counting from the page 0. So 0, 1, 2, 3, 4, and so on. So we are looking at the 9th page in the memory, and we are looking at 256 bytes in the memory. Let's do reset, and let's do a run here. You see that this part of the memory hasn't changed. Let's take a look now at the 600. Reset. You can see some data here. This is the actual information that represents these commands up here. We got the commands in, and then what the assembler did, assembler turned these commands into opcodes, and these opcodes are represented by hexadecimal values here. The thing that we need to understand is that what we call assembler is not the last step in programming the CPU. The last step is actually hexadecimal values that are inputted in the memory. Also, the way that memory inside the CPU is structured is defined by the designer of the CPU and the designer of the system that you are working on. This particular system has been designed in such a way that it uses a memory map that starts from 0, then the first or the 0 page is empty. The first page is something that you can use for whatever reason you want. So the 0 page is the first page. The first page after this, so the page from 100 to 1FF, is the page that you can use for whatever reasons you need. And then locations from 200 to 5FF are represented by this black square here. This black square is basically the pixels starting from location 200, then to the end, and 5FF, and the top leftmost pixel is the first location, so location 200 in the memory, and this location is 5FF in the memory. It goes from left to right, and then just continues on, and this is a fundamental solution to how to create the easiest possible graphics. If you put a value into the byte or the location in the memory, this location is going to contain this byte, but also if this location is between 200 and 5FF, this is going to be shown on the screen as a pixel. So this program, as we are going to see, is going to just fill the first 3 locations on the screen with different values, and then it is going to show them as pixels or points in the graphic memory. If you need to know which value corresponds to which color here, you can take a look at the notes. Notes are down here, and it is going to explain that your locations are going to be 200 to 5FF to the screen pixels. The values that you can input are this. So these are different colors that you can use. So you can create relatively simple graphics by using your assembly language directly in the simulator. Touring around the user interface, I mentioned these buttons are used to control the way that the simulator is running right now. This part is where you put your program in, or this is the part where you write your assembly application. This part is the monitor that shows you the location in the memory. This black screen or black square is just mapped memory that shows you the locations and shows you and enables you to do the graphics. And the last thing that is left is a debugger. Debugger enables you to always monitor the current state of the CPU. So you can monitor the entirety of the CPU, the A, X, and Y registers, stack pointer, program counter, and then these are flags. So the flags are also denoted by N, V, this one is not used, B, D, Y, Z, and C. So you can see different flags and how they are set right now in the CPU. Also, you can use the step and jump tool in the debugger. Why? When you press run here, you're going to run the entire program. If you press the reset, you're going to just reset the state of the processor and start prepare it to run the program from the start. If you do the hex dump, you're going to see how your program looks like in hexadecimal values. So basically, you're going to get this. I'm going to show this, but you're going to get this. Disassemble is going to show you how this hex dump directly translates to instructions, because different instructions, the same instruction can use different opcodes, and sometimes you need to disassemble the program that you have in the memory because you didn't write it. You can either get it directly in hexadecimal form from somebody, or you can just create something in the memory and then try to understand what this part of the memory does. If you use the debugger, the thing that you're going to do is you are going to be stepping into the application. So you're going to be running it one location at a time, and you are not going to run it in its entirety. This enables you to understand how the application works completely. So you are going to be able to understand how each different instruction works and what the different instruction does. Now let's try to explain what is the connection between this, and this. First, I'm going to explain line by line what this thing does, and then I'm going to do the demonstration and do step-by-step running of the application. And after that, I'm going to be doing the explanation of what these things mean, or how what is the correlation between, for example, this one and this one here. So let's get down to work. The explanation of the instructions is easy. We're going to be using just two of those, LDA and STA. LDA means load to accumulator. So whatever value is here is going to be loaded into the accumulator. In the previous video, I mentioned that you can use different signs before the value that you intend to use, because these different signs means different things to the assembler. The hash sign or hashtag sign means that you are dealing with the value that you want directly accessed. So in this example, this means 1. You are not referring to a location in the memory. If you omit this sign, for example, like in this thing, you are referring to a memory location. So just using a number is going to point you to the memory location, and this means that you are trying to store something from the accumulator to this memory location. If you omit the $sign, the $sign represents the hexadecimal values. So if you omit the $sign, you're dealing with decimals, and this is something that we are rarely going to do. Main reason is the simplicity. If you are dealing with hexadecimal in everything inside the simulator, it's much easier to think in hexadecimal and to put the values in hexadecimal than to try to always in your head translate from decimal to hexadecimal for no particular reason. So the first instruction is LDA hash $01. This means get the actual value of 01, so 1, and put it into the accumulator. Next line is going to do the STA, so store from accumulator, and this is going to store the value that you have in your accumulator, the register accumulator, or the A register, and store it to this location in the memory. Note that this number is 16-bit. Memory is addressed, when we are dealing with 6502, memory is addressed as a 16-bit number, because we can address 64 kilobytes of memory. But all the rest of the values and all the rest of the registers are 8-bit. So this is an 8-bit number, so just a byte. This is 2 bytes. Also, as I mentioned, note that this is a location because it doesn't have a hashtag before it. Next thing that we're going to do is we are going to load the accumulator with the number 5. Then we are going to store the value to the 0201. Then we are going to load the accumulator with the value 8, store it to the 0202, and this is going to be it. Why are we going to do this, and what is going to happen? As we said, the locations 200, 201, 202 represent top left most pixels here, or the pixels represent the locations. So once you put these values into the locations 200, 201, 202, 3 pixels should appear here with different colors. What I'm going to do is I'm going to go and show this, but I'm going to show it first by running the application and then by stepping into it. So running it step by step. So if I press run, you see I have 3 pixels here. These 3 pixels here are different values. So 1 is white, 5 is green, 8 is some sort of a brownish, probably light brown or something like this. Also, I can see here that I have some values in my processor. This is because the processor itself has stopped working after it went through this code. So after it reached the last location, it stopped. The values that have been left inside it are the 8 in the accumulator, x and y is empty, stack pointer is also not set, so it is on the top of the stack, and the program counter is pointed to 0610. 0610 is this location here, so this means basically that the program counter is expecting that it's going to start running, the next command that should be run is here, so it stopped here basically. Also, none of the flags were set. This is something that we need to also discuss. The way that computer knows how to start working, so where the application should start and how the application should start, is determined when the computer was being created. What this simulator is presuming is that once you are creating your application here, this application is going to be assembled, and then it is going to be stored at location 600. This is not something that is a standard. There are different versions of the 602 that start from different locations. Locations are dictated by the people who design the processor. So, for example, if the processor was designed by somebody who wanted to create, use it as a microcontroller, so no video memory, he can perhaps start on location 600, 800, 200, whatever. In this particular case, the memory map that the designers wanted to use was designed in such a way that he used different pages. So first page was empty, second page was empty, third, fourth, fifth, sixth, seventh sixth page were used as video memory. Then he created the space for the assembly language or the code itself. And then everything else after this can be used to store your data. This is just a decision made by the developer of this assembler. It can be different. But once you create your computer, and when you decide where when your program should start, from where your program should start, for this example 600, this means that when I press run here, I'm going to go to the location 600, and then I'm going to run whatever is stored in the location 600 and treat this as a command. The debugger is going to do the same thing. So they're going to start on the same location, and this is the thing that you need to understand. Also, if I do a disassembly of this, and this is not going to show, I'm going to be turning this information here into this, and I'm going to be showing what different commands do. Let me just say that let's correlate this thing and this thing. So while using this assembly, let me just get this thing zoomed in. So the first command is LDA hashtag $001. This means stored number 1 to the accumulator, and this gets translated into A901. A901 means A9 is actual opcode or operation code for the LDA, and this opcode is referring to directly storing this value into the memory. So this instruction took 2 bytes. Then the next instruction is 8D0002. This is our STA 200. 8D is the opcode, and 0002 is the value that he's using to reference the memory. Now we need to talk about a thing called endianness. So little endian and big endian. The way 6502 is storing the numbers is the opposite of what you would think. It is not storing the numbers from left to right. It is taking the number, this particular case 0200, so 200, and it is going to swap the bytes. So the last byte, the least significant byte, is going to be the first one to be stored, and then the most significant byte. This is called little endian. Little end first, or little endian, is the way of storing that is usually used by 8-bit processors. Since this simplifies the addition and all the different operations quite a lot. You don't need to think about getting the carry across and working with the carry. What you can do is you can just simply store the value as least significant byte first and the most significant byte second. And when you add, if you have a carry, you just carry it on and go from left to right. This is the same thing that you would do on a paper. If you are adding numbers, you are not adding them from left to right, you're adding them from right to left. So the same thing applies here, but what the processor does is he's switching the values in the memory, so you don't have to jump across the memory when you're adding, or for that matter, subtracting values. So A901 first command, 8D0002 second command, then again A905, this is this LDA, 8D0102, so 201, A908, 8D0202, 202, and that's it. This is the entirety of the application assembled, and this is the way that it's going to be run from left to right. I'm going to now run it into the debugger and try to explain what is happening step by step. When I first press the step button, the first thing that is going to happen is I'm going to actually be executing the first command. You can see this because my value of the program counter was 600, now it's 602, because program counter always points to the next instruction that is going to be run. So the value of accumulator has changed. A has become 1. X, Y, stack pointer weren't changed because this is the way this instruction works. And the thing that you also need to have in mind always is to understand what is the different what are different instructions doing to different flags. So the flags haven't changed in this particular case, but they are going to change depending on the value that you put into the accumulator. We're going to go through this a little bit later, and I'm going to try to explain to you where to find this information if you need it. So we loaded the accumulator with a value of 1. We did the program counter has moved. So now the processor is expecting to be running the next location. So the location here. This is location 600, 601, 602. So the processor is expecting to run this next instruction. Let him do it. And now he switched to 605. This is because the processor, while reading the operation code, so this part of the instruction, the actual instruction, knows how many bytes this instruction took in the memory. So it is able to move the program counter for the appropriate amount of spaces. So this one moved the program counter for 2 spaces. This one moved the program counter AD, moved it for 3. So depending on the operation that you're performing, or the instruction that you gave it to perform, the program counter is going to move itself. Now it's pointing to the next command, so A9. But before that, we can see that the accumulator hasn't changed, and the only thing that has changed is the memory, and this is denoted by this pixel here. So we show the pixel. If you do another step, accumulator has become 5 because of this instruction, and then program counter has moved for 2 locations, and then after we do a step, we are going to be storing this location number 5 to location 201. We can see a pixel here. Then we do the number 8 to the accumulator, and then we do a step, and then we put this pixel here, and that's it. The thing that this simulator also makes easy for us is that it is not going to run indefinitely. Normal processor requires you to stop it. This processor, this simulated processor, is going to automatically understand that the program has ended. It is going to stop. Normal, regular CPU is going to just keep on running and increasing the program counter by 1, trying to find the next command. And this is something that we are going to be introducing when we are going to be dealing with the more complex simulators. But since the idea of this video today is to just introduce you to how 6502 works, we are not going to go into some or the rest of the details, simply to make things easier on you. So now we have done this. We see how the application works. The way this ebook works is that Nick is introducing different things at different times, and this is basically the first thing that he wanted you to do, so to acquaint yourself with how the simulator works. And you can see that this is the thing that needs to be understood. You can also scroll to the memory, you can also scroll to the notes and so on, and there are some of the things that you need to know. Okay, now there are some exercises that we are not going to do now, but you can always try to do them. Changing the color of the pixels is easy. You just change the values. You can also change the location in the memory that the pixels are going to be drawn to. And this is changed just simply by changing the value for the STA function. So your application is going to be storing to a different location in the memory. You can add more instructions to draw out the extra pixels, and this is something that we are going to do once we start doing the loops. Now, let's take a look at another example. This one is a little bit more complicated because it introduces a set of commands that we haven't used, or instructions that we haven't used up until now. And the other thing is that it is going to be more complicated because it tries to introduce you to the idea of stopping the program. Also, there are different things that you can see written here, and these different things are called comments. Whenever you are in the assembly language, usually semicolon is the character that tells the assembler that whatever is left of the semicolon is the instruction, whatever is right of the semicolon is the comment, and this comment should be used to comment the code and make the code easier to read. This applies not only to the code in this example. This applies to everything that you write in assembly. Once you start working in assembly, you are going to be creating complex things, because there is nothing more other than the instructions and the comments to explain to another person what your code is doing. So there are no hidden functions, there are no hidden things that you can call from the memory unless you create them, and everything that you do needs to be explained, not because of you, but also because of other people. If you want to create something, you need to explain what you did and why you did it, because once you start learning how to code, you can create quite complex things in the assembly, and this is going to require you to make notes on what is happening inside your application and why is this particular command used here. So always use the comments. This one is heavily commented. I think in a normal working thing, or in a normal working application, what would happen is you wouldn't be using the comments this heavily. You would just say For example, you wouldn't comment break, because break is a command that says, okay, now stop. Tells the process to stop. Now, let's see what this one does. It loads the hex value of C0 into the A. Then it does a transfer. TEX and INX, or ENX and TAX, transfer the this one transfers the accumulator to the X register. So it basically moves the value from A to X. INX increments the value. So it just adds 1 to whatever is in the X register. Then we're going to ADC C4 to the A register, and then we're going to stop. What we did here is that we put a value of C0 into the A register. We transferred the value from A to X, so we basically copied the value from A to X. Now X holds the value of C0. We increased the X register by 1, so it's C1, and then we added C4 to the A register. The reason why we did all of this is to show some important concepts. So let's go through them step by step. I'm going to assemble this. It is going to assemble itself correctly. And I don't have any need of monitoring the memory. I'm just going to be using the debugger, because this is not about the memory, this is about the registers. It doesn't load to the memory anything. So first, when I start, my program counter is 600, so this is the start of the program. And when I step, the first thing is going to be that I'm going to be loading C0 as a value into the accumulator. Then I'm going to be stepping into it, and I'm going to be transferring value A to register X. Notice that I'm not moving, I'm transferring. Transferring means that I'm going to be copying the value from A to X, and A is going to retain the value that I have already used. So this thing is just copying the value, and now X contains the same value as the register A. Now I'm going to increase the X, so X becomes C1. And then I'm going to add the value of C4 into the ADC, into the accumulator. This means add with carry. So this means that this value is going to be added to this value, so C0 to C4. And the thing that is going to happen is that if we are overflowing, or if the carry happens, the carry is going to be shown. So let's step. And let's see what happened here. C0 plus C4 is bigger than 256. So what happened is that the processor is going to tell us, okay, the value that you got is 84 in the A register, but you also have a carry set. So this value isn't 8-bit, it's a 9-bit value. So you basically overflowed or overfilled your byte. It doesn't fit in your byte that you have available for the storage. So this number is bigger than 256. And this is normal. This is the way that when we detect things that are happening with the addition, because obviously as soon as we add any two numbers that are bigger than 1 byte, something needs to happen. We need to know, because this value is not correct. This is not 84, it's bigger than this. Also note that we have set N flag, and the reason for this is because the 6502 has a peculiar way of thinking about numbers, because it doesn't know what you're trying to do and it doesn't care. The way they kept the complexity to the minimum is that they created a way in which the number that you have stored in the memory is whatever you think about it. So if you're storing 84 in the memory, this can mean the number 84, so 8-bit unsigned value, or the first bit of the number, so the leftmost or the highermost bit, is going to represent the negative number if it's set to 1 or a positive number if it's set to 0. So this can also mean a negative value that is stored in the memory. In this case, you're dealing with 7-bit signed or unsigned values. So you're going to have 7 bits available to deal with the number itself. And then you're going to use the 8-bit or the leftmost bit to denote the positive or negative value, so that you know that the number that you have stored is either positive or negative. This enables you to have more or less 2 values stored at the same time. Depending on how you read it, the value is going to be either a negative value that is going to be a positive or negative value, so it is going to be signed, not signing as in has a signature, but signed as in has a sign, so it's a positive or negative. And then you're dealing with values from minus 127 to plus 128, or the number that you have stored is from 0 to 255, but this value is then unsigned, so you're not storing the sign inside it. Since the processor doesn't understand what you're dealing with, and he doesn't want to understand what you're dealing with, your processor is going to just simply give you both solutions. So it is going to give you the value here in the accumulator, and it's going to say the first bit has been set, so this is a negative value. If you're treating it as a negative value, okay, fine. If you are not, also fine. The processor doesn't care. Sometimes when I'm lecturing, I'm trying to explain to people or to students that the processor is an extremely agile, extremely quick, extremely stupid piece of technology. Because what it does is it executes one instruction by one instruction, not caring about what you thought, what you think, and what is happening around it. It is just looking at the particular instruction, doing what it says. So whatever you want to do, you need to think by yourself and then turn it into instructions. And after that, it is going to be executed the same way every time you run it. And this is the idea of programming. Although, to be honest, sometimes it doesn't look like this, because sometimes it looks like some of the programs are running by themselves and not thinking about anything else other than this. But this is just the way that programs designed it and the way the technology works. The technology has become more and more complicated basically each iteration of technology, and this is one of the reasons why we are dealing with 6502 right now and not with assembly for the latest generation of Intel's AMD processors. Okay, now let's do another thing. Let's step to another example that we're going to do this today, and this is going to be the last one. What I want to deal with right now is the way that 7-bit and 8-bit numbers, or unsigned and signed numbers, are treated in the assembly in 6502. So, as I mentioned before, your computer is storing the numbers in bytes. Byte is 8 bits, and if we want to store the number from 0 to 254, this is completely fine. So if I say FF here, this is a normal hexadecimal number, a normal hexadecimal converter. This is going to convert a hexadecimal to different values. So this is the thing that we are looking for. So unsigned 8-bit integer, this is the value of 255. So old ones in the binary code. The problem that we have here is that if we want to denote if this number is positive or negative, we need to do something. And what we need to do is we are going to be dealing with numbers in such a way that we are going to tell it, okay, this number is negative, by using the first bit. So the first bit in 8 bytes, it is going to be the value of the sign of the number. So if the first bit is set to 1, it is going to be the negative number, and if the first bit is set to 0, it's going to be a positive number. When I say first bit, I'm thinking about and talking about the first bit on the left. In binary and in any other normal notation of the numbers, this is the most significant bit. So we are using the most significant bit to denote the number for two reasons. First, because the minus is on the start of the number, but the more important reason is because this enables us to use the numbers normally and then have a problem only when we are dealing with conversion from 7 to 8 bits. So what is this problem that I'm talking about? The problem is this. If I use the biggest value that I can do in 7 bits, so leading 0 and then once all the way to the end of the byte, the thing that I'm going to do is I'm going to be noting 127 as unsigned and 127 as a signed number. So far so good. But if I want to add 1 to this, so this is going to be 128 as a unsigned number. But if I want to add 1 to this is going to happen. Unsigned number is going to be 128, first 1 and then leading 0, then the rest is going to be the zeros. And this leading 1 is going to be denoted as a minus sign, and then all the zeros after this are going to be treated as a number. Specifically, since this number should be signed, so the first one denotes minus, this is the lowest number that you can write down inside the single byte. So minus 128. Why are we starting from the location? So 127 plus 1 turns into minus 128. Why? Because next addition, so for example, this is 81, so 80 plus 1 is going to become minus 127 and so on. So we are, by adding 1, we are decreasing the value as it should be. Also, we are increasing the value here. This is also called the double complement of the number. Look it up, because this is something that you're going to be needing when we are dealing with the numbers. But this is the way that the processor treats the numbers, and this is the way the processor is able to show you what is happening with the number itself. Now, let's also show something else. Let's show how does this look like in the assembly. So I'm going to do a version of the example that the assembly, the ebook is doing, and I'm going to load the value of 7F to my processor. Then I'm going to simply just add the value of 1. And I'm going to assemble this, I'm going to debug this, and I'm going to step. So 7F is the accumulator, the flags have not been set. Then I do another step. Now an interesting thing has happened. Accumulator has turned into 80. And this is okay, because 7F plus 1 is 80. But the flags have been set. And the flags have been set both the N and the V. N means negative, V means overflow. This is the exact thing that I showed you in the types converter. What happened is that the processor realized that you ran out of space, so your number that you're trying to store in the 7 bits is no longer be able to be stored in the 7 bits, so you now require 8 bits to store the number. The number itself is represented as a byte, so this is the value, but it is warning you that currently the number has turned into a negative value and it has overflowed. So suddenly your 7 bits are no longer enough to store the value of the number, so now your number is bigger than what it used to be. What does this mean for you? If you were dealing with signed numbers. And if you're thinking about adding 1 to 127, this should be 128, because you haven't changed the sign, because we didn't want to change the sign. You just wanted to add value 1 to 127. So these two have been set together to tell you that this has been turned into a negative number because over the overflow. So that you understand that this is not a negative number if you don't want it to be. And this is one of those things that you're going to be needing to think about when you're dealing with 602 and with any assembly at all. Now let's do the example that the ebook has, because there is something also pretty important here. And this is one of the most common mistakes that you're going to be doing by doing assembly. This looks almost exactly like the example that I was doing. Okay, it is starting with the value of 80, then it is storing this value to location 1, and then it is adding to the accumulator. But note that this number here is not the number 1. This number here is the location 1. So what this is actually doing is storing the number 80 hexadecimal. So first leading 1 and then all the rest of it's zeros. Then it is storing this to the location 1, and then it is adding whatever is in location 1 to the accumulator. Since it just stored the value 80 here, we know that basically what is happening is that we are adding 80 plus 80. So we are adding two numbers that are both 8 bits. So we are going to have an overflow, obviously. And what is going to happen is that since we are dealing with a particular number, the result is going to be 1 followed by 8 zeros. So a 9-bit number that is going to be followed by 8 zeros. And this means that the result is going to be a little bit confusing. If I do the debugger, we have number 80 in the accumulator. It's a negative number according to the processor because the leading bit is 0. And then we are storing it to this location 01, and then we're going to be stepping into it. What happened is that accumulator has turned into 00. This is expected because the number is, as I said, 9-bit number, leading bit, and then 8 bits after this are 0, so this is a 00. But it has turned from negative to positive because there is no longer negative sign. The first bit is 0. It has turned on the overflow because we did the overflow. We changed the value. If we are dealing with 7-bit values, we change the value. The result is 0, and we have a carry. So this is one of those things where you need to pay attention to not only to what is happening inside the accumulator, but also understanding what is happening with the flags, because you want to understand how the processor is dealing with this and what happened to the negative values. Since we, according to the signed arithmetic, we added 2 negative values, so 80 is a negative value, so 80 is minus 128, as we showed here. So 80 is minus 128. We added minus 128 to minus 128, and what we ended up with is 0 and a carry. So we need to take care of those things, and this is the reason my overflow flag has tripped, is because we did something that in signed arithmetics doesn't make sense, and we need to understand what has happened. And the most important thing is that we need to check for it. So while you're doing the assembly programming, you're going to be need for checking on different things that are happening while doing arithmetics, while doing comparisons, and so on and so on. I'm going to finish today's talk about 602 assembly with this, and in the next episode I'm going to talk about how to create short loops and how to create different branches inside the programming. so that we can do different things in the assembly language. Thank you for being with me. This is still the ThatITShow. I hope that next week we are going to be back in the studio with Vedran, and the next episode is probably going to be published together with me talking with Vedran about different things. Thank you.